The standard model of redshift is that redshift of light from galaxies is caused primarily by the Doppler effect. The redshift is related to the distance of galaxies by the Hubble Law, distance proportional to z through a proportionality constant. The Hubble constant in this equation plays a pivotal role in current cosmology. The Big Bang model calculates several observations using this law and on the isotropy and homogeneity of the universe. Several studies have been conducted to find the Hubble constant by relating the distance to galaxy with distance calculated by other indicators. The method using Cepheid variable stars is accepted as the most accurate for distances up to about 30 megaparsecs. The Hubble Space Telescope Key project provides the best correlation for distance versus redshift. Wendy Friedman and her team conducted the HST Key project. If we plot the calculated redshift using the Hubble Law and decalculated using Cepheid variable stars for 32 galaxies in the HST Key project, and where Zm here is the measured value, the correlation coefficient for this is about 0.80. This is a poor result, but is still better than other teams' data. The standard model is basing its entire structure on the meaning of redshift. The 0.80 correlation coefficient is a poor basis for such an important understanding of the universe. The deviation of the recession velocity of a galaxy from the straight line of the Hubble Law is ascribed to a peculiar velocity of the photon emitting galaxy relative to Earth. The deviation from the Hubble Law is the only means of determining the peculiar velocity of a galaxy. The average peculiar velocity for all galaxies is assumed to be 0 on a scale that the universe appears homogeneous. That scale is greater than a few hundred megaparsecs, if at all. This video applies the scalar theory of everything to develop an equation for the calculation of z and to test the equation using observations of galaxies with Cepheid distances. The stoe suggests spiral galaxies are sources and early type galaxies are sinks of the scalar potential field. You may search John Hodge stoe, photon diffraction, and others for backup here. Photons are a column of Hodge with a plenum between them. The energy of the photon depends on the plenum density, which is established by the sources and sinks. An equation is derived that recovers the Hubble law for cosmological distances from data that is anisotropic and inhomogeneous. The resulting model is used to calculate redshift of particle photons for a sample of 32 galaxies of the Key project. The calculated redshift has a correlation coefficient of 0.88 with the measured redshift. There are 3 zones in the Cepheid result. The first zone is actually a blue shift. That, of course, is not allowed in the Hubble view. The second zone is basically in our cluster. The distances here are confirmed by tip of the red giant branch method. And the third zone is further out, such as in the Virgo cluster. This is very poor correlation, almost no correlation with distance. If we take the close galaxies, which are the first 2 zones, and plot a line there, we see it's actually a pretty good correlation. But further, it's a good correlation to these distant galaxies out here on the high side of the measured galaxy. The problems then are here, which are in the third zone and with small measured z. The stoe suggests the plenum density along the photon's path changes the energy of the photon. The possible relative velocity is secondary for the redshift. The scalar potential field due to sources is this equation, where epsilon is the source strength and r is the distance. We have a proportionality constant. The scalar field due to sinks is the same kind of equation, where eta here is the number representing the strength of the sink. You may note that that is less than 0, that's a negative. If we plot the scalar potential from NGC 4535, we get this kind of a line. The galaxy is on the other side of another galaxy cluster. Here's the galaxy. This is the photon going near the center of the cluster, which are a bunch of sinks, and later on it goes through a shell of source galaxies. Okay. After that, we have a long path of intercluster travel, and then a 1 over r relationship. This 1 over r is basically, the rho is proportional to 1 over r from our galaxy, and you can see how it fits the curve. Here's another galaxy, NGC 1326a, some elliptical galaxies, but other than that, the 1 over r curve seems to work. The 1 over r effect seems to dominate here. The causes of the change of energy of the photon are the total amount of rho traveled, the change in the number of HODs lost or gained, the change in the plenum content between the HODs and the photon, and the contribution from nearby galaxies we don't see because they are across the center of our own galaxy. The sink-like characteristics of matter were considered part of the luminosity to source sink strength. The resulting equation, where Z, here is the calculation, this is x. The k's are proportionality constants. The d, p, and f are functions of the scalar potential, and VE is related to the possible galaxy on the other side of the center of our galaxy. You'll note that there are 7 constants in this equation, and we're looking at 32 data points, so we should be able to determine the k's. Here's the plot of our calculated z versus the measured z. The correlation coefficient is 0.88. You'll note that the problems are on the low end of the measured z in the third area of the graph. Plot distance versus the exponential factor x for our HST key project sample galaxies. This straight line is here, minus 2700x minus 1. You note the minus 1 here, we don't get a 0 interface. Again, the problems are on the low end of the third area. At large cosmological distance, the z approaches 500, which is the limit of what we can get. The Hubble Law is recovered without assuming the universe expansion. That is to say, we have the equation, and we make that proportional z by making the distance large, meaning this is ignored. With a 1 sigma correlation coefficient of 0.93, we have a Hubble constant of about 110. Due to the 1 over r of the scalar potential, the dz relation for distances greater than 20 milliparsecs recovers the Hubble law, where the value of c over h0 is a proportionality constant, without invoking the counterintuitive expansion, isotropy, or homogeneity of the universe. That is, without any requirements of the Big Bang model. The 0.88 correlation coefficient may be improved if there are unaccounted objects. The mass around galaxies was considered part of the source mass-luminosity ratio. If the galaxy is not mature, the luminosity is not an indicator of strength. And of course, morphology of the galaxy may enter in. QSOs have been ignored because popular wisdom indicates they are too far away for this sample. However, If Halton-Arf is correct about where and what QSRs are, they would impact the measurement favorably. Here are other links.